Okay, so I mean, and one of the reasons why I kind of wanted to do this was that I got a lot of questions, especially related to Exadata nowadays. That how does Oracle choose between a direct path read scan, or and the smart scan then on Exadata, and the regular buffered table scan. So this was the question which made me think that, okay, I have to elaborate this further. All right. So, but I cannot just start from that. I actually have to start from some internals, that how do full table scans work, right? And okay, so how do full table scans work? And then we will look into this ORA error and so on. So let me see. I had one note. Martin, I see you asked that do I have two screens running, and yes, I do. But right now you should see my blog page in Crow. All right. So let's just make sure that you see the right thing. So now you should see SQL Plus with welcome in it. So okay, so just give me a second. So okay. So for some weird reason, I had paused my screen, or it was the tool. So sorry about that. So as you see, this is a hacking session where some things can go wrong. So now you should be able to see my SQL Plus. Okay, cool. Now it works. Don't worry. I didn't show any SQL Plus or any demos yet. But what I wanted to show to you is this is where you get my scripts from. You see, these are the Windows or Unix zip files you can download. And I'm just going to briefly show this as well. Okay, so let's start from how do full table scans work, and then we will go on to all of the other interesting stuff. Okay, so let's create so let me see. Let me create a table space. I think I'll just start from that. So I'm just going to create a table space for because I want to pick a uniform extent size. All right. I want to pick a small extent size. I'll just say 64K. Let's see, external local. Okay, so does anybody recall the syntax? Okay, local size. Oh, okay, so I don't even remember that. So I gotta check that. So because I want to create a table space where we have a bunch of small segments. So let's see if anybody remembers. Next. Next. Nope. Let's see. This is something else. It's uniform size one. Extra management. Okay. Size. Right. Okay. So we have a table space test, and it has only small extent. So let's create a table there, right? So I'll just say create table T. Let's drop it first. Okay, so create table T, table space test. I'm actually going to call it something else, T lots extent. As select star from DBA source, one of the bigger, sort of views when you want to, generate some test data quickly. So basically now we should have this table with, tens of extents or, even more. So it's going to take a while. All right. So and let's see. If I look into DBA segments, right? DBA segments shows me the owner, segment name, something which is going to be important. I'm going to show you header file and header block. So basically, this for every segment, DBA segments stores where is the header block. Sorry, where is the table header block? In which block it is, in which file, right? So this is how Oracle knows where the segment starts from. Both for tables and the indexes. All right, and of course we have extents here. So I have a little script which shows me some of this data. So it's 84 megabytes in size, and oh, interesting. I don't even query the number of extents. So let's just say select from DBA segments where segment name equals this. All right. So you see this table actually has 1,300 extents already. Okay. So some tables may have tens of thousands of extents. And I'm not going to even touch the topic whether it's a good or bad idea. Nowadays the amount of extents is not really a problem, compared to back in Oracle 6 days. So don't worry, you shouldn't really be worried about that. But basically you can have, since Oracle 8, you can have any number of extents in a table or in a segment. I'm going to explain how this any number works as well. But you can create a table where you have 10,000 extents. So extents can be anywhere in the table space, right? So there must be some place where information is stored, that where these extents physically are located, right? So this place used to be the segment header block, So it still is partially true, but back in Oracle 7 days, if you worked with Oracle 7, you may recall these magic numbers like that. If you were running on an 8K block size, then you could have, I think it was 505 extents per table. Or I may recall it wrongly, but it may be a bit shifted. And if it was 4K block size, then you had 121 extents, and something like that. Okay, so this was because, I don't remember exactly this, but the number of extents per segment was limited because all the extent pointers had to be stored in the segment header. So basically every segment had only one header, right? But the header block size is limited, right? So you only have like 4 or 2 or 8K or 16K or something like that, right? So the smaller block you have, the smaller header block you have, the less extent pointers you can store in there, right? The extent pointers are the data block addresses, that where the next extent starts from, right? So this was why the number of extents was limited in Oracle 7. But in Oracle 8, Oracle did, and they added something. So in addition to the segment header, now they also can create extent map blocks. Extent map blocks into the segment if the existing extents don't fit into the segment header, right? So you may recall that there used to be these kind of tables like the views were DBA extents, right, and DBA free space. Okay. So in dictionary managed table spaces, they were based on UAT, used extents table, and sys free extents table. So in dictionary managed table spaces, this info where the extents were of a segment, this was also additionally stored in these tables and used for space management later on. But if I query these views right now, or these tables, base tables right now, let me open a select count star from sys used extents, right? Free extents. Nowadays Oracle doesn't even use these tables. So basically, with locally managed table spaces, the data dictionary doesn't know where the extents are. So nowadays, the data dictionary only knows where the segment headers are, really. And it knows how long, what is the total amount of blocks in that segment. But the data dictionary does not know where the actual extents, the pieces of that table are physically. And this is what gets us now to the full table scan topic. That, if you want to do a full table scan through the entire table, you obviously must know where the extents are, that which blocks you have to read and scan through, right? And how this is done, and actually how it was done back in locally managed table space days as well, that when you do a full table scan, then your session will go and open the header block. Basically, it will find the file ID and the block ID in the file, and this is the segment header of your table. And now your session will open this segment header block, and inside that header block we have the extent map. And this extent map then tells us exactly where the extents physically are. So this is going to be a pretty important thing we use here in the further examples. So basically, in order to do a full table scan on any segment, a table, index, or materialized view segment or whatever, you have to go and open the header block first. You will do a single block read and open up the header block. And once you have done the single block read, of course it's needed when the block is not in cache. Once you have done the single block read, you will know exactly, how many blocks there are in the table, below, or sorry, this is how many blocks there are, in the table, also above high water mark, and this is how many extents there are. So it's enough to only open up the segment header, and you will already know how big the table is. Okay, so I'm just gonna, just for fun, I'm just gonna dump. You see, when I run the seg command again, when I query the DBA segments, right? So this is the header file and header block. So if I do alter system dump data file, block this, all right? So this dumps me the header block contents into a trace file. All right, so let's see whether the audio and everything is okay. So as if asked that, what if the header block gets filled up, right? So and this is exactly why the extent map blocks were created in 8.0. So basically in Oracle 7.3, when you reach the maximum number of extents because of the header block got full, then you couldn't extend that table anymore. Your table could not grow because there was no more space to put the next extent pointer in the segment header. So and this was why in 7.3 and before you had all these reorganization tools which kind of recreated your table with 1 extent or 10 extents and so on, bigger extents that time. But that's all not relevant anymore. Okay. So, but let me just show you that you can actually look inside this trace file, and let's see. This is a block dump. Let me search. Go to the right place. Okay. So so basically, I just wanted to show you this that basically when you open up the segment header block, you have all this information at your, all this information available, like how many blocks we have, how many extents we have in that segment, how many blocks we have in that segment in total. And also one important thing is the high water mark. You see, it tells you, where is the high water mark of the table? Because sometimes you have like the table, the segment size is at a gigabyte, because you have allocated 100 meg extents, but the high water mark is slightly lower because you haven't filled up the last extent yet. But basically, you see, the total number of blocks in this table, in this segment, is this 10,776, but the high water mark is really here. So it's saying that there are, so this is how many blocks we would have to scan through when we did, if we did a full table scan. So I'm not going to go into the low high water mark and high water mark. So this is ASSM specific stuff, but this is important. So especially this high water mark thing here. So this is how Oracle decides whether a table is a big table or a small table. So I'm gonna get there later on. How the direct path read decision is done, right? But this is basically what Oracle uses mostly to decide whether a table is big one or small one. And depending on whether it's a big or small table, then it will either decide to use a direct path read or a buffered read. So we're going to get into these details later on. But basically, this info comes from the segment header. So it's important to know that the direct path read decision is not made by the optimizer. So basically, optimizer only decides whether to do a full table scan or not. And now when you actually start the full table scan has started. Basically, we will then read the segment header block, what you see here. So we will do a single block read to read the segment header block. We will read it in, and then we will look into this number of blocks of that segment. And based on the number of blocks and the buffer cache size, and also based on how many blocks are cached already of that segment, then we will make the decision of a direct path read or not. But I will get into these details later on. But basically, what's important to know is that you will always have to read up to 10. There is a special case as well, but you will have to read that single block first before you even decide whether you go direct path or not. So and this info we get from segment header. So when I scroll down, this L2 and L1, these are all ASSM related things. But you see, this is where the extent map starts from, right? All my extents are 8 kilobytes in size because I forced the uniform extent size, right? So we are not going to have like a few smaller extents and then bigger ones and bigger ones like the auto allocate does. But you see, the first extent is living in this block. It starts in that block and it's 8 blocks wide. So this is the data block address. So I can actually take this number and if you want, you can use my script called DBA. DBA means data block address. You see, so this is the internal, hex format, of the restricted or of the relative data block address. And when you convert it using the script, for example, then you see that it's in file number 6, and this is the block. This is where this extent starts from, and it's 8 blocks long. So, all right. So I'm just gonna cancel that script. It can show you what the object ID it is if you're logged on as sys as well. Okay. So, and now let me go to the end of this. Oops. Okay, so now we have run out of space in this segment header, and now we have auxiliary map. Let me see if this is, let's see, what is this? So I think how this works here is that Oracle has pulled all the extent pointers from the block header, and then it probably went to the to the extent map block. So basically, when you in Oracle 8.0 onwards, when the header block gets full and you still want to allocate more extents, then Oracle will create extra extent map blocks. So it basically will put them somewhere else, wherever there is, the next free block in the table, so it can allocate that block for the extent map, and it will just put these extra pointers into this separate block. Okay, so let's just do this. So we have this table T lots extents. So I can just, it doesn't have any indexes on it. So we can just do alter system flush buffer cache to make sure it's not in buffer cache, that nothing is in there. And let me just change the trace file identifier, and I'll just enable SQL trace just to show you that this is how it that this is how it works. Okay, so Stefan asked that what is the maximum size of that extent map in a block? Well, it depends on how big your block is, but there is no practical limit, because if you want to allocate 1 million extents, then you will just have hundreds or maybe 1,000 extent map blocks across the whole table. But of course, I wouldn't want to have 1 million extents. But if I do see 1,000 extents for a table, I'm not worried at all, right? Unless I actually see that these extents are so small, like 64K, so that instead of megabyte reads, reading a megabyte at a time, we start reading 64K at a time. Anyway, I just want to show this very simple query. Right, I have enabled SQL trace, so this is just a 1046 trace. Okay, so this count is done, and then let's just disable the trace as well. Okay, and now when we look into the trace file, we should see a single block read first. It looks like the dynamic sampling kicked in. So I think I'll just repeat this thing. I don't want the dynamic sampling to kick in, because it will mess up my demo. It will already prefetch data. So let's just do this once more. Just gather table statistics for that table, and I will say flush buffer cache again. I enable trace. Wrong one. I will just write the output into a new trace file. So this TI script just creates a new trace file. So whatever I write after that. Okay. So now I have gathered the stats. So the dynamic sampling should not kick in anymore, and I have enabled the new trace file, and SQL trace is on. So let's see how do we do this time. So now I want to go to this file. All right. Let's see, where does my query start from? Okay, here it is. All right. So this is where I started the query. It parsed, it got executed. You know, in the execute phase, a query really doesn't do much. It just allocates some memory structures. And you see, so the first IO related wait is DB file sequential read. So it's block number 6, sorry, it's file number 6, block number 130, right? And you know, we only read one block. And you know, this is the object ID of our table, so I can just verify it. You know, this object ID from the trace file, yes, this is our table. Okay, so nowadays, I mean, not nowadays, you know, so since early versions of Oracle, I would say Oracle 6, this is when it was rewritten, Oracle has always had to first do a single block read or access the single block, the segment header, and find out, you know, where are the extents of that block. Of course, in real life, when you do many full table scans, then you know the segment header block may remain in the cache, may remain in the buffer cache. So you know, unless you do a flush buffer cache, you won't see this single block read because it's already in cache. But anyway, after this block was read for that table, for that particular segment, then Oracle checked, okay, how many blocks do we have above the high water mark? And it saw that, okay, it had like 10,000 blocks. And then it checked, okay, how big is our buffer cache? And it sees that buffer cache is, let's say, 20,000 blocks. And it sees, you know, and this is when it decides, I'm going to talk about that algorithm later on, but this is when it decides that, hey, I think this segment is a too big segment. It's a too big segment for reading it into buffer cache because it would flood the buffer cache. It would pretty much, you know, flush out other useful stuff. And you know, if the segment is bigger than buffer cache, then it doesn't make sense to cache it at all, really. Because if it's bigger, then by the time you reach the end of the segment, you already have flushed out, you know, the first blocks anyway. But I'm going to talk about this algorithm later on. But anyway, what you see from here, Oracle has done a single buffered read, and apparently it has decided that, hey, I want to do a direct path read because I see all these direct path reads following, you know, the same file, and we just start ongoing. You see, this is where the block header was, and this is where, you know, where we started reading from. So we just read 13 blocks, and here we read 15, 15, and so on. Okay, and you see this. If you Google for this async descriptor resize, I've written a blog entry about it. This is basically, it has appeared when Oracle adjusts how many asynchronous I/O slots this process can use. So direct path reads use asynchronous I/O for prefetching data. You know, so basically, you know, it's not like you read a megabyte and you wait for that read to complete, and once you're done, then you read another megabyte. Actually, with asynchronous I/O, Oracle can you know, prefetch multiple megabytes. So while it's processing the first megabyte, the fetch for the next megabyte is already being serviced by the OS. But anyway, so this is what I wanted to show you. This is how Oracle knows and decides that whether a table is a big one or small one. And you know, and makes the you know, following decisions after that. That, you know, what is the caching policy? Should we do a direct path read or a buffered read? And now there is something important, which you may want to write it down, or at least remember. So this thing here is done for every segment in your query. So this is a decision which is done during runtime for every segment in your query. So if you join two tables, then this block header or the segment header is opened for both tables. You know, when we start scanning them, you know, if you do a full table scan, you know, one table may be small and another one may be big. So it may be that the small table will be read with the buffered reads, and the big table will be read with the direct path reads. So So this decision of direct path read versus buffered read is it's done during every execution. So it's done during every execution, and it's done for every single segment you access. It's done for every segment. So even if you scan one table, you have one table, but it's partitioned. Let's say it has 100 partitions. It has 100 partitions, right? And let's say 50 partitions are small ones and 50 are big ones. So when you scan through all the partitions, then Oracle will go, when it goes to the next partition, it will open up that partition's segment header. Every partition is a separate segment with the separate header, right? So it opens up every partition segment header when it reaches it and checks, okay, this partition is big, I'm going to scan it with direct path read. And the next partition is small, I'm going to scan it with buffered read. So you actually can have cases like that, and I'm going to demo in that. So this is done for every segment while you execute the query. It's not a property of execution plan. It's not somehow stored into execution plan that I'm going to do direct path reads for everything I read. No, this is done separately for every single segment, and each partition is a separate segment. Okay, so let me use my favorite tool, Snapper, to kind of show how you measure that. So I'm just going to run Snapper on my session 16, right? If you don't know what Snapper is, then just Google for that and you'll find out. All right. And I'm just going to run the same query again. And it probably used direct path reads again because the previously it used direct path reads, which means that it didn't cache anything, right? If you use direct path read, you read directly to PGA and you don't cache anything for future queries. Okay. And this is what Snapper told me. So it ran for 5 seconds, sorry. Snapper, I ran it for 5 seconds, and yes, indeed, it still reports me direct path read wait events. So as you see here as well. Okay. And one of the important things here is this. Table scans long tables. So whenever Oracle sees a long table, what it thinks it's a long table, which is greater than 10% of the buffer cache. Or let me get back to this. I'll show you with the demo. Then you will see this. When Oracle decides that, hey, this is a long table, it increments this by 1 for every scan. So of course, if I only ran one query against a non-partitioned table, but if I had executed one query against 10 partitions, I would see this go up by 10 if all the partitions were big. So I'm just going to create a small label, which is just a copy from dual. So if I do select star from T, I'm just going to show what happens, right? So so I run Snapper again, and I run this query, which is against a small table. It happened so fast that this ash top wait events, top SQL section didn't even capture anything. But you see, as I scanned the short table, Oracle reported, hey, it was a short table. Okay, so it was smaller than a threshold plus some calculated logic. So, and you see, if I scroll up, this was the case with the big table, or it was a long table. That's why this table scan long went up in the session statistics. And also, as Oracle chose to use a direct path read, you see, it also reports this, that yes, we did a table scan against a long table, and this also happened to be a direct read table scan. So this is another way of kind of finding out whether a query is doing direct path reads or not. and you know, you see it from these metrics. Okay, so but even though, you know, despite this small table, I can actually, let me flush the buffer cache, alter system flush buffer cache. I think the tracing is still on, so I'm just going to run the same query again against the small table. So, and let's see, let's look into the trace file. From dual. Okay, I gotta disable the trace, then it will flush it. I think some of it was still in the buffer. Okay, what the hell? I just repeat this once more. I just flushed the buffer cache. I enabled the trace. Maybe I had already disabled it somehow. Okay, so select star from T. So this should be the small table now, and let's disable the trace as well. So it would flush whatever is left in this output buffer. Okay, so now I'm puzzled. Let's see what's going on here. So I enabled SQL trace, select star from T. Okay, I think there is, I have to exit the session. I'm not going to waste your time in it. So there is yet another thing. So because this statement was in the cursor cache, then in 11.202, it doesn't always show the query when I parse in the text for some weird reason. Anyway, but this is my query. So I wanted to show you this. This is my table T. The object ID is table T. I can actually query it from DBA objects, right? So it's the system.t. Okay, so basically when I ran my query, it actually first went to the segment header block to see how big the table is, and as it saw that, hey, this table is really small from there, you know, the high water mark number is there, then it decided that, hey, I'm gonna do a small, you know, it's a small table, I'm gonna do a buffered read. So there's no direct path read here. So I can kind of alter this a bit. I will say alter session set serial direct read equals true, sorry, always, which is actually the same as true. So this is what I use for testing, or you know, Kerry Osborne is using it as well. And okay, so so people gave me feedback. So I was looking at the wrong table. Yes, of course. Anyway, so I found the wait events anyway. So I searched for dual in the trace file, but actually I wanted to select star from T. So anyway, I showed the wait events still. And what I will do here is I'll just run the select star from T again. But I will just in case add a couple of add this here just to look it up better. All right, so where is my, okay, I have disabled the trace, so let's just get a new trace file. All right. And I don't even have to flush the buffer cache or anything. Well, unless something goes wrong here. Because thanks to that parameter, we should always force a direct path read. Although in some cases I've seen some weird things happen. Let's see. Okay, the trace was on, and we can go to this file. All right, so okay, we do see, so this actually gets weirder now. So it looks like the direct path read did not still kick in. So we could actually validate that. You know, this is where you see, this is a shortcoming of SQL trace. You only see the wait events and a few extra statistics. But now if I want to see whether this direct path read actually kicked in, I can again use snapper. I just run snapper on my session, and now I run that query again. All right. So I ran that query again in the other session, and you see direct path read did kick in as it says. But what's interesting is it says that we did one physical read IO request as well, you know, for the actual data. But what's interesting is, and in this case it does show direct path read wait event. Let me just repeat it with SQL trace. Maybe there was some buffering issue again. So just do test 4, and I will say disable the trace, and this should be our trace file now. Okay. You see, this is our query. At least in the previous case, Snapper told us that physical IO was done. You see, you know, it told us that direct path read was done, one, and also that we did a physical IO request, and we actually read, you know, this is 8 kilobytes. So we did a physical IO, but the trace file still doesn't show it. So that's actually that's weird. You see, this is where we close the cursor already, because, you know, this is when the execution plan stats are dumped out, you know, these numbers here. So, you know, this, I hope to demo this with small table, but I wouldn't be surprised if you actually have hit the bug or some issue right now where SQL trace just doesn't dump this out. You know, what kind of shows that direct path read code path is issued is this, because, you know, when this async descriptors are resized usually when you do direct path operations, you know, either reads or writes. So that's actually a good example where SQL trace doesn't show us what $systat does. It shows that we did do a physical read, and we actually waited for direct path read. Okay, so I'm actually going to come back to this topic. So all this time I kind of wanted to illustrate this, that for every segment, every partition in every table, right, all of them have segment headers. And these segment headers tell how many blocks we have in that segment, you know, below high water mark. So we know how many blocks we will have to scan through if we scan through that segment. And the decision of whether we do a direct path read or not, this is done for every execution for your SQL, and it's not SQL execution specific. Actually, while you execute that SQL, then every segment you scan through using a full table scan or fast full index scan, you know, so this decision is done for every segment. So Oracle will open the segment header block, and we'll see how much work it will have to do, and then it will decide whether it does a buffered read or direct path read. And this also means that you know, if you do have a lot of partitions, you know there are some systems which have 1 million partitions, and, you know, in different tables, right? So this means that you actually will have to have 1 million segment headers and perhaps more extent map blocks in buffer cache. And these are accessed using a single block reads. Okay, so I'm gonna just switch to another topic for some time, and then I'm gonna get back to this and hopefully show you these parameters which control what is a big table and what is a small table. But for now, remember these wait events. When you see direct path read wait event, there is some direct path read going on, and also, this tells you, whether the Oracle considered the table big or small. And again, sorry, this is not the table size really. This is the segment size. So actually, that's pretty interesting. You may have a table which is 1 terabyte in size, but it consists of 1 million partitions. So every partition is, what is it, a megabyte, right? So if you have 1 million partitions times a megabyte, then it's going to be 1 terabyte, right? So my calculation may be wrong, but you get the point, right? So the table is huge, but every single partition is tiny, and you will end up with a lot of tiny, scans, small table scans. You will actually end up doing buffered reads because the partitions are smaller. Oracle doesn't look into the full table size. It will look into the partition size if it's partition table. It looks into the segment size. Okay. So Jeremy asked that why didn't we see this the physical read operation in the trace file, that maybe the single block which we tried to read was in buffer cache. Yes, normally that would be the reason, that if the blocks are cached, they don't show up in the SQL trace. But in my case, I had used this parameter, which should force using a full. It should force the direct path read even for serial sessions. But as I said earlier, I've seen some funky issues with that. Exactly, in some weird cases, it seems to be ignored. But in our case, when you look into Snapper, then it did show that we did a physical read. And by the way, this physical read was also a direct path read. Because when you do a physical read for a buffered read, when you do a physical read which is gonna populate something in buffer cache, then you will see physical reads cache here. But as we see, the only I/O, only physical read, only block read. So this actually is the number of blocks read. Actually, so this is the number of I/O requests. This is the number of blocks read. But we read only one block, and that one out of this one is actually read for direct path read into the PGA. So if you see, there is another stat called physical reads cache. So this is incremented when you actually do buffer cache, physical reads for or through buffer cache. Okay, so I'm going to stop with this topic and I'm going to get back to this, but I'm going to talk about some other topics first. Okay, so basically we looked into how do the full table scans work, right? And we looked into this part as well. How does Oracle decide between this buffer and direct path read scan? I'm going to get back into this topic. I just want to cover the other stuff first. We'll look into these parameters which control things here. All right. So by the way, there is one more funny thing here. It is that so this is the underlying table under DBA segments, right? So whenever you do a full table scan on a table, right, then you will know. I mean, how does Oracle know where is the leading block or where is the header block of that segment, right? So this data is stored here in this table physically. Okay, so and this data is actually cached in the dictionary cache as well. So we don't have to always go to a recursive query and go here. And this is the block. This is for every segment we have. This is the starting file number where the header block is, and this is the block number, right? So the DBA segments view is just a view on top of that table. So this data allows us to know exactly where other tables and segments start from. So when you do a full table scan. By the way, when you do an index scan or index unique lookup or index range scan, right? So then you won't have to visit segment header. Index range scans don't have to go to segment header. So there is a special case in Oracle that index root blocks are always guaranteed to be immediately next to the segment header. So this is kind of hard-coded into Oracle or specially coded into Oracle. When you create an index, obviously it will have an index segment. It will have a segment header, and right after the segment header, this is where the index root block is. And as this is sort of hard-coded, then whenever you do an index range scan, Oracle again can find out, okay, where is the index segment? It knows that, hey, it's in file number 1, block number 5, and it knows, okay, I gotta go to the root block, which will be block number 6. It's immediately after the segment header. So even if index root block splits, then Oracle has some special code in it so that the new root block will still be placed as the first block after segment header. And the old root blocks which split, basically it's moved away, or basically the blocks under it will be somewhere else. Okay, so also indexes rely on this data as well. Index access relies on this data. But I wanted to, there is like a chicken and egg situation here. That, if this is the ultimate table which tells where the other tables start from, right? This table tells where the other tables live, where they start from, and this allows us to access it. So who tells Oracle where this table itself lives? Isn't it a chicken and the egg situation? In order to find out where is that dictionary table seg $, we will have to go to this table and find out where it is, right? So there is a chicken and egg situation, and seg $, is a special table in the sense that there is a pointer, there is an object called bootstrap $, right? Bootstrap segment. You may remember it from old DBA classes. So there is a special bootstrap segment. So let's see what we have in here. So I just made it a bit better readable. Okay, so this is a bootstrap segment which contains DDL statements. So these are kind of virtual DDL statements in the sense that these tell Oracle, when you start up Oracle, they will tell where the segments reside. It doesn't really create the new segment like this. So basically, if you look into this, if you scroll right, all the way to right, let me just select all of it. So it defines the columns of that segment, and in the end, it also defines what will be the object number and the table number in the cluster. Okay, and but when I look, so cluster is the physical storage where we have this, where files and blocks are. So I have to search where is this cluster definition created. Okay, so this is where the cluster, nope, this is not created. So this is where this cluster is created, where the DBA segments itself lives. All right, and lives in. And let me look into this cluster. So check this. I'm not sure how well you followed this, but basically there is a bootstrap segment which contains sort of like a declaration, SQL-like declaration statements which tell Oracle where the segments actually reside, where the special segments reside. And basically the seg dollar is a table in a cluster, and that cluster itself is defined here. It lives in file number 1, block number 192. So basically, the bootstrap segment contains the information where all the special tables are, like seg dollar. But the bootstrap dollar, bootstrap dollar itself is a table. So during the startup, how does Oracle know where the bootstrap dollar itself lives, right? So this is where we go one step even back, further back. And when I do alter, let me just change the trace file, alter system dump data file 1 block 1. Let's dump the data file header block. So this is the data file header, and okay, sorry, I'm stupid. So for data file headers, we should use dump file header. When you don't remember these commands, then just do ORA debug ORA debug dump list. What kind of dumps are possible? Dump list. And I think it was called file headers. I think it was this. It kind of got a bit more complicated. So you'll have it all in the video, so you don't have to write it down. Basically, this dumped the file header information. Let's just make it into a different file. Let's just do it once more. So now it's in the O2. All right. So okay. So I'm not sure whether I will be able to find this out from here. Perhaps this perhaps I'll have to use a different way to dump this block. But basically, where I was getting at is this. So let's say if you wanna scan a table, orders. If I want to do a full table scan on table orders, then how do we know where the orders table lives? Well, we will know it thanks to seg dollar table. So how do we know where the seg dollar itself lives? Well, we know it thanks to the bootstrap dollar, which is processed during instance startup. And then it's kind of sort of like executed during instance startup, but in a special way. It just defines where the segments are, right? And how do we know where the bootstrap table itself is? Well, there is in file number 1. We have a special section which I wasn't able to dump out, but there will be a basically the file number 1, the header block actually has a pointer data block address number, that where in this file number 1 this bootstrap segment resides, and this bootstrap segment then will define, or in there we have the info of how to find the segment dollar itself, and from there we can kind of access any table we want already. Okay, so basically this thing is processed during the startup. So we don't have to go through this green part every time we do a full table scan. This is processed during the startup, and using that we will populate the data dictionary cache and whatever million other memory structures. So once we have started up, we don't have to go through this anymore. So we already have the segment dollar data, either on disk available, or some of it will be cached in dictionary cache as well. So this is the sequence of how Oracle makes sense out of the millions and billions of blocks in the data files. How does Oracle know where the tables are? Okay, so, and now I'm gonna take a sip of water, and I hope to try to not spill it. And we will continue with this. It's gonna be like 5 minutes only, and then we will go to this error, and then whatever time we have left, we will look into this direct path read decision in more detail. Okay, so I managed to not spill this time. So my table is a bit sticky, so I gotta fix that later on. Okay, so there is a data object ID. So this is like a different topic. So it's related, but loosely related. So now we'll just switch to a different topic. There is an object ID and data object ID. Why are these used? I know at least one reason. I'm sure. I mean, there may be more reasons. So when I describe DBA objects, okay, come on, what's going on? All right, you see something is stuck here. So this is really good chance to demonstrate some troubleshooting. So I'm not just gonna restart my Oracle here. Let's see. My session is 16. So actually, this we'll take a step back and we'll look into something else. My session is 16. What's going on? First thing is what I do is I look into SW often, or I could run SW just queries $v session wait. So this is the query I just showed you that. SW immediately returns me and tells this session is currently waiting for this wait event. So it's basically waiting for so it has sent a break to the client. This happens when an error happens, sometimes when an exception happens, or to tell the client that, hey, an exception happened, clean up your client-side call structures, because we didn't complete that last query or call properly. An exception or problem happened, right? So this is why this wait event happens. But when I look into this, and this should be really fast, just a network round trip. But in my case, you see, I've been already 99 seconds in this wait event, right? And it grows. So basically, this indicates that my client side has a problem, or sometimes it's a network issue as well. Because this wait event means that Oracle sends a packet back to my client and is pretty much waiting for a reply from the client which says that, yes, I understood that the problem happened, and I'm gonna, I cleaned up my client-side structures related to the latest database call. But this happens sometimes. I suspect that I have hit Control-C somewhere here earlier. Or maybe an exception really happened. I suspect I've hit the Control-C or some issue, because when you play around with Control-C, then this sometimes messes up this connection like that, so that your client side doesn't really want to accept that packet anymore. So, so I'm still stuck. I know what's going on. So, my session is not doing any work. It's been waiting for 160 seconds for this wait event. So in this case, I would have to see what my client is doing. But this window here is my client. So, I see that my client is still running, right? But I think previously when I hit some Control-C, this may have messed something up. So in this case, I'm not going to restart my database or anything, but my client has gone crazy. So I will have to kill the client actually. So I'm just going to close the window. Or actually I do a Control-Z and I will do kill -9 last command. % is the last, it's the command that I just put into background. Okay, so this was a quick intermission. Whenever the session is stuck, use session wait or snapper or ash, which uses the same data pretty much. And look whether the state is waiting, and if it is, what wait event are you waiting for, and for how long you have already waited for that. Okay. So back to this topic. What is the difference between the object ID and data object ID? Okay, so no more break waits or client weirdness or some exceptions. You see, every object has an object ID and data object ID. So why is this? One reason should be that sometimes you have a let's see, let's look into the seg dollar. One reason is that you can have clusters, so that you can have a cluster object which it's a physical segment, and now you create the multiple tables inside that cluster. People don't do it that much anymore, but in the past, they were popular when you wanted to get this last bit of performance out of some of your queries. But anyway, you see the object ID of that seg table, dollar table, is 14, and the data object ID is 8. So the data object ID is pretty much the segment's object ID, and this is the logical object ID. So if I show my table T, this is the table that I just created today. If it's a regular table, then there is like one-to-one relationship between object ID and data object ID in the beginning when you create it. So you see the object ID and data object ID are the same. But with clusters, this is the segments. This is the clusters, segment object ID, and then this is the logical tables object ID. So this is what this object ID is what is used for dependency management. That if a PLSQL package depends on a table, then there will be some pointer to this object ID somewhere. This is like a higher level thing, logical dependency management and so on. Let's see what else do we have in the seg dollar. I think we probably have like a you see these tables which were used in the old days, the used extents and free extents. Oracle wanted that this extent info would be clustered together with their corresponding segments. Then these tables were created inside that cluster, right? You see, this is the table object ID, this is the logical object ID, and in this case you see the cluster ID, or the physical segment where the table actually resides is this. You see, it's the same number 8 here. It's different here. This is a different case. So when multiple logical objects share the same physical segment, this is when you have the case where you have one data object ID and different logical object IDs. So I guess that's one main reason why this separation was created. And I'm going to show you, why this is, needed, or what is the other benefit here. People can do various operations with segments. Indexes can be rebuilt. Tables can be moved, right? So this is my table, what I created. Let's create an index on it. Okay. You see, this index has also, the table was created with a lower object ID. Index now has one higher. But what I want to show you here is if I do alter index I rebuild, right? And now I query DBA objects again. You see, data object ID went up. The logical object ID is still here, because we cannot really change that logical ID, because we may have, maybe in library cache we have things which point to, which reference things by object ID. Maybe, in library cache perhaps less likely because they use memory at register, but there are lots of other structures. Like, also on the DBA dependencies, PLSQL packages may use, or do use object IDs to reference, different objects. But this object ID, it kind of has to grow because, when you rebuild an index, you're actually creating a new segment. You're creating a new segment. You are building the new index in that new segment, and then you will drop the old index segment. And this is why the data object ID has to change, because we are dealing with a different segment now. And soon in the context of this error what I mentioned, I'm going to show you why is it needed to kind of signify that this is now a different segment. So whenever you rebuild an index, this data object ID goes up. You see, whenever I do a alter table T move, this is also a DDL operation, which really creates a new segment. It copies, it pretty much does like a create table as select into a new segment, and then just gets rid of the old one. And you see, this is where I previously queried that table data, right? So the object ID is the same, but the data object ID has gone up, because this, 38 has been used by the index already, then we just pick the next one. So whenever you move a table, the data object ID for that table goes up as well, because essentially we are having a new segment. So it's a new segment, and new queries executed after that the operation has completed, should use the new segment. Okay. And one more thing, if I do a truncate table T. You see, the truncate also drives the data object ID up. The logical object ID still remains the same, but the data object ID changes, because truncate also creates a new segment, really. Sorry, it's not correct to say in the sense that it doesn't create a new segment in a different location, but it will just reformat your existing segment header. It will just reinitialize it pretty much, so that your existing range of blocks, they will actually kind of belong to your new segment now. So it's like a new segment, but it's in the same place where it used to be. But also this has to, Oracle wants to show that now we are dealing with a new segment. So there is, if you dump a data block, you will see there is in each data block header you have the data object ID in it. So you don't, in each data block header you have things like or actually let me dump something, so it's going to be more fun that way. So create table T1, select star from dual. Okay, T to T. All right. Just log on, you get the formatting back. All right. So this is a table, and this is where it lives. Header file and header block. System dump data file. Okay. Oh, sorry, I don't want the header. I want the actual data block. So I'm just going to take the. I can also say things like block min this and the block max. You know, whatever a range of blocks. So all right, and okay. So when I dump the block, you know, there's plenty of material in the internet which explains what all of these fields mean. This is a data block, and you see this is the segment's data object ID. This is a hex number, right? So this is stored in each block. In each block header, you know, with the other metadata, we have this info as well. So you see, if I convert the hex number to this 91242, and when I now check what is the data object ID here, you know, this is a new table what I just created. You know, it's the same data object ID. So basically, so this is where I will kind of start moving now towards this error what we will look into now. You know, every block header has this data object ID in it, and this helps Oracle to do a sanity check that whether I'm reading the right blocks. You know, even if somebody has done an alter table move, you know, or truncate and has reused that space, and my query is still running, right? Then this helps Oracle to do a sanity check whether I'm reading the right blocks. I just said something which may be very interesting to you, which is actually relevant. I told you that you can actually truncate the table where the query is still running. You know, there's a query against the table, and you can, you know, it's still running, you know, some report. You can truncate it. You can do a partition exchange. You can do alter table move even. You can drop the table as well. You know, let me demonstrate this to you now. So let me do it on table T. Select star from, let's do a create table T as select star from all users. You know, nice and smallish table. It's not that big. Select star from T. Okay, we have like 40 rows in here. Nice. Okay, so I will do this. A little bit of PL/SQL hacking. Open C, sorry, var C ref cursor. I will create the bind variable C, which is actually a ref cursor, and I will say open C for select star from all, select star from T. Okay, how ref cursors work. You know, I don't waste time on SQL trace. You can repeat this and see what's done in which phase. But how ref cursors work, and this open here, is that basically we open the cursor, we executed the cursor, and ref cursors also fetch the first row. So Oracle has this cursor is still open, and Oracle has fetched the first row, and it has stopped there. So this is how ref cursors work. So this query is still actually sort of running. You know, I'm not executing it; it's still open. All right, and now I can do a let's say I do a drop table T. Okay, and now I'll say print C. So you see this, I have dropped this table T here, right, which my query is referencing. But when I print C, now the rest of the query is executed. And you see the query still is able to fetch the data from the table. So you know, I have dropped the table, but the data blocks are still there. You know, when you drop a table, Oracle doesn't really do much. You know, you can even drop a table which is in a read-only table space if you like. Well, actually, I just gotta do that. So you know, this is also pretty fun. So so you see, I have this table space, something with lots of extents. Tx. Oops. All right. Kind of illustrates what the drop is doing or not doing. So it's in system. So, and it's table space test, right? You see in which table space this table is, right? And I will say alter table space test read only. Okay, table space test is read only where this table is, right? And I will say alter table this guy, not alter, sorry, drop table this guy purge, and it's under system. You see, I just put the table space into read-only mode, but I still am able to drop a table from that table space. And this is because when you drop a table, Oracle doesn't go and somehow reformat the blocks or anything. Oracle is very lazy. You know, you can see what happens when you enable SQL trace. You know, you will see all these recursive queries against, and you know, DML against data dictionary. When you drop a table, Oracle just removes the table metadata from invalidates it in library cache, and you know, invalidates it in the dictionary cache as well. And of course, it removes the metadata from data dictionary. So this drop really, it didn't touch this table space at all. It just removed some data dictionary metadata. And but all the blocks are still there, right? And now back to my example here. You see, in this case, you see, I already executed the query. I already parsed it. I opened the cursor. I parsed the query. I resolved all the objects. I already found out, hey, we are accessing this table T, you know, before it was dropped, right? We dropped it later on. We already resolved where is the segment header. We opened up the segment header, you know, and we read the first row just to see, you know, whether we get anything. And so we already did all the work to find out where the segment header is. And now when I did the drop table here, this only, you know, modified data dictionary. But our query here, when I ran the query, when I actually, you know, this print now will actually fetch all the rows from that ref cursor. This guy doesn't have to go to data dictionary anymore, because we already know where the data is. We already have done the lookup work before the table was dropped. So this is one example that, you know, Oracle does allow queries to keep running, you know, as long as the data blocks are there. Of course, if I try to run the same query again, now that I have dropped the table, well, see what happens. Well, I have dropped the table, so obviously now the right thing happens. We will get the error because we don't find such a table anymore, right? But Oracle allows us to keep running the query when the data blocks are still there. We know where the segment header is. We can kind of, you know, keep reading that, and, you know, read the info that where are the next extents, and then we go to the actual blocks. But now, of course, you will immediately have the question that what if somebody overwrites the data, right? Well, we can do this as well. So let's do the same exercise again. Create table T, and we will I will gather table stats as well, just to avoid the dynamic sampling, which may kind of mess up something in here. Actually not. I just realized that the dynamic sampling kicks in during the parse time, and it's not used afterwards, so it wouldn't actually mess up anything. But anyway, and now I've created the table, and let's do this trick again. I will say, oops, sorry, that's the wrong exit. So again, I opened the cursor, and let's see what happens if I do a truncate table T. All right. So I've truncated the table, and when I say print the ref cursor, well, this is the first case where we get this object no longer exists error. What happens here is that that the truncate actually goes to the table. It actually goes to the segment header, and it reformats the segment header block. The drop command does not do that. Drop command is so lazy, so it doesn't do that. But truncate does. So, and now that even though in this case, when I ran the query like this, or when I kind of opened the query with this, of course we went to the segment header to find out where the blocks are. But there is this special case that Oracle sometimes revisits the segment header. And one of the cases where it revisits the segment header is if you have multiple fetch calls. So what Oracle did in this line, it issued parse, execute, and the first fetch, just to get one row to see whether it gets anything, right? And then it returned. But the next fetch, this is where the next fetch call was sent, and this is when Oracle went back to the segment header again. So it doesn't kind of remember where the extents are across fetch calls. If you have many fetch calls, each fetch 100 rows at a time, then it will still go and visit the segment header. You can actually trace this out and so on. Some of these things change by versions as well, by the way. Slightly, but the key point is the same. So this is a case where we got this error. So, and one more reason when Oracle goes to revisit segment header or extent maps, if we have so many extents, is that Oracle doesn't remember all the extents. When it opens up the segment header, then it doesn't fetch all the 5,000 entries from there. It actually fetches 10 at a time. So it basically opens the segment header, fetches the location of 10 next extents, and then it scans through these extents. And if you want to fetch more, you want even more data, then it will go back and takes the next 10 extents info from the segment header. But this error happened because we had reformatted the segment header, right? So the truncate actually reformats the segment header. And even if you use the reuse storage option, the reuse storage only keeps the extents for you, but it still will, reformat the segment header and, move the high water mark back to the beginning. So, but this is not all. I want to show what happens with drop as well. So let me just set the array size smaller. So let's create the table again. Oops. Okay, I truncated the table. So let me just drop table T. Let me just go through the same thing again. I create the table. I will open this cursor. And I already said, let me just say it once more, set array size 10, which says that only fetch 10 rows at a time. I also say set page size 10 because I want to set pause on. Basically now it will pause every 10 rows. So I will have to press enter and I will see whether we get this error immediately or not. So let's say reuse. I don't remember whether this, okay, this is the syntax, so we just, keep the storage, or, don't release any extents back, to the table space. And let's say print C. Okay, now it's hung because, oops, actually it wasn't hung, so it was already fetching. Anyway, so we hit the same thing what I showed. I just thought that whether it would, if the array size would be smaller, if we fetched less rows, whether it would actually, whether it would, let's see what I wanted to say now. So basically I wanted to see whether in truncate case it would return some rows like it will do in the drop case, but no, because the next fetch will go to the segment header and it sees that we have a new block there. Basically the data object ID in the block header has changed. This is when this error happens. The data object ID has changed. So when we open the query, Oracle will resolve. It resolves that, hey, table T is object ID 5 and data object ID is 10 or something. And throughout whenever it runs the query, or when it now fetches from the query, then it knows that it wants to read from data object number 10. And now when it actually goes to the segment header, it opens up the block and it checks the header and it sees that, oops, the data object ID is 50 there. So therefore, this object no longer exists. This block has been overwritten by somebody. Therefore, the old segment doesn't exist. So it's perhaps better to say segment no longer exists, not the logical object. The logical object, the table T logically is still there, but physically it has changed. Okay, and I'm going to run through this once more with the drop because when I ran drop previously, then the whole query finished. When I started showing this thing, I dropped the table and I ran the query and it finished, no problems. So, but let me show. Let me see if I can use this small table for reproducing this. So I will open the table T, and now I will drop table T. Okay. In the first demo, now when I issued the print statement, it showed me all the rows because all the blocks are still there. But I will say a purge I think this may not work because I may have purged other things as well. So the space, the new table that I'm going to create now may use some other space, but other block range. But let's see. Okay, so I hope that this segment reused the same block. So I could have checked, but it should work. So print okay, we still get the same error immediately. So this is actually a good example. So now in this case, we dropped the table, we purged the recycle bin, and I created a new table which happened to reuse that block range. So Oracle saw this. It tried to read the segment header, I think in this case, but it saw a wrong data object ID or a newer data object ID owned by some other object. So again, we get this error. But I actually want to show you this a bit. Let me show you it a bit differently. I'm not gonna use the ref cursor. I'll say create table blah. No. Actually, this is good. Create table blah, right? So it's from DBA objects. It should be big enough for my purposes. So remember, I said set page size 10, array size array size 10 pause on. All right, so we will only fetch 10 rows at a time, and we will pause in between. So I have the control of how fast the table is scanned. And now I will just say select, let's say object ID from blah. Okay. So now it waits for me to press enter, so it will just show the first page full. And now it shows the next 10 rows. So the array size is 10, but the page size is also 10, but it also includes the header here. So anyway, so you see, I can slowly fetch more rows as I want, as I want to go, as the array size is 10. Okay, so the table block is still there, and let me go to the other window now. So in the other window, I will say drop table block. I'll just say purge as well. Okay. Now the squaring still works okay. You see, I'm pressing enter. You know, it returns more rows. Okay. But now I will create some table again. Table. And I hope that this, you know, normally Oracle reuses the last block range, apparently. I'm sure there are special cases, but in this case, likely this new table reused some of the old blocks. So it actually overwrote some of the old blocks with its own data object ID. All right, so let me, you know, I'm just going to show that, you know, this is, oops. So when I press enter, we still get some rows back. But let's see, if I just continue pressing, just hold it down. Aha. You see, this is what I wanted to show to you. So, I scanned, you know, I held my enter down, so we fetched 10 rows and 10 rows and 10 rows, and we displayed, you know, more and more rows. So basically, we were still able to display some rows, you know, even though the table had been dropped. So, but at some point of time, now we get this error that the object no longer exists because I had overwritten some of the blocks, and perhaps, you see, perhaps we returned 2,000 rows, right? Perhaps let's see. So I'm just thinking, what would be the reasons why we see you know, some of the rows. So one reason is that, you know, not all the blocks were overwritten by us. So, and of course, if the array size is like 500, then we would have like may have a full buffer of 500 rows to display before we go back to the table. But basically, at some point of time, we opened another block in that table. So perhaps previously here, where everything worked okay, we opened up then a block, and you know, this still had our data because it was not overwritten yet, right? But then we opened up the next block, and we did a sanity check to find out, you know, whether the data object ID matches the data object ID of our segment, you know, which we want to access, you know, when we started the query. And at some point of time, we get this error: object no longer exists. So this comes from when there is a mismatch between the data object ID you know, we are looking for when the query started, right, and the actual data object ID of that block. And this situation only happens when somebody actually drops the object which you are querying, which you are still querying, or when somebody does DDL, like, you know, partition exchange as well. You know, and this is a common case with partition exchange, that, you know, you have long-running queries, sometimes which take like 5 hours or, you know, maybe more. And now you do partition exchange, and then you drop the old partition which you exchanged away. when you reload more data, or for whatever reason you do that. So this is when you have this error, because when you have a partition table, you start your query, then Oracle will read these partitions as they were when you started the query. So when your long-running query is running, and sometimes later you will do a partition exchange, you switch to a partition with a table, right? Then Oracle will still read the original segment. This is basic read consistency. Oracle has to see the data as of when the query started. When the query starts, Oracle takes the current system change number. When you open a cursor and you do the execute, Oracle checks what is the current system change number, and it will try to see all the data, or it will actually have to see all the data as of that SCN, as of that system change number. It uses undo segments for that. And of course, if there is not enough undo data to roll back to old enough a snapshot, then you will get the snapshot too old error. But it also ensures that it will use the same segments. So when your query starts, and even if you do partition exchange, or whatever, alter table move, or alter table move partition and stuff like that, then it still reads the old segment. But if you actually drop that old segment now, which was exchanged out of the table, you drop it and you overwrite it with some other data, this is when you get this error. So this is why when I do partition exchanges, if the space allows, I don't drop these exchanged tables immediately. I'll drop them the next day, or 12 hours later. So if I have 11-hour queries which run for 11 hours, I would want to drop this table 12 hours later or even later. So not immediately. So I don't want to kind of get rid and overwrite that data which some long-running query still wants. Okay, so this hopefully explains why this error exists. Of course, there are bugs as well. Search for that in Metalink, then it's full of examples, or there are many more reasons. But I will also show you this error. This is similar. So let me repeat this similar exercise. I will say create table blah, right? And I will say create index all right. And instead of a full table scan, let's use an index range scan now. So I would say select index. I just use the simplest hinting here, and I say object ID. Let's query something else. Owner. So we want to go to table as well, where from blah, where object ID. So this is the indexed column, right? It's bigger than 1. Let me just check whether the execution plan would be correct. Yes, we would use an index range scan. Let me just set size 50. Okay, let's do it. Okay, so yes, it would, at least the explain plan says that I would use an index range scan, and with the row IDs, you see, from the index I take row IDs of the rows which match this condition, right? In number 2, right? So index returns row IDs usually. It can return some columns as well. But basically, then we take these row IDs and we feed these row IDs by this row source here. Basically, this table access by index row ID, it takes the row IDs what the index range scan has returned to it. And from that row ID, it knows which data file to go, what is the data object ID, and then which block to go into. Okay, so table access takes the row IDs and goes to the corresponding blocks. Okay, so let me run this query now. Okay, so I hit enter once, so it fetched. Let me just do it in a better way. I'm just gonna select row num as well, so we see how it increases. So I will fetch the first array full of data. Okay, I don't fetch anymore. And now I will go and drop table blah, right, purge, and let's get rid of it. And now I will create another big table which hopefully reuses the space of the table and its index as well, because the index was automatically deleted, dropped as well with the table. Okay, let's hope that this works. Let's hit enter. Oops. All right, so we didn't get lucky here. Of course, now, okay, I think I know what happened here. So, this is yet another thing to know. You see, let me see that. Let me just run this query. Set the pause off. Okay, I'm just going to run this query and. Oh man! So we of course we dropped it. So I think what happened here. Let me just okay. So I'm gonna show this as a last thing, and then we can move on. So basically, I think what happened here was the cardinality feedback of Oracle. I used explain plan command to see what would be the execution plan, but I suspect Oracle actually switched. No, it didn't switch because we had the index hint which should force it. Let's see, we get the index. Yeah, I think, so I'm not going to put your time under it. So I have demoed this before, but I somehow have forgotten this. But basically what I wanted to show you here is that whenever you see invalid row ID, this is also similar reason. Because, when you have a, well, perhaps this works with global indexes. You see, when you have an index, when you have a global index on a partition table, what happens? Row ID has the data object ID in it, then it has the relative file number in it, and it has block number, and it has row number. So this is the extended row ID, right? Maybe I should have done this test on a partition table with indexes, because on partition table with global indexes have this part here in them as well. So and what I did here is I started a query which did an index range scan here, right? But basically when you see this error, what happens is that when your query runs and now somebody drops the partition or exchanges the partition and drops the table, resulting table, and basically if the table data blocks get overwritten, then if you still have some index blocks accessible, let's say the index blocks were not overwritten, let's say the index was in a different table space, and I didn't overwrite, I didn't create any big segment there. So now you do the index range scan here. The index blocks are still there, and you can range scan them because nobody has overwritten them. And now you find the matching row ID. Now you will find, okay, there is a row ID which points to this table, but the table has been overwritten already. because I have created this big segment there. And now we will take this row ID and we will go to that table with this information. And we will go to the table block. We will go to this file, we will go to this block, and then we will open up this block. And one of the first things we do, we check whether the data object ID in the block header is still the same where the index row ID points us to. You see, the index extended row ID points us to data object ID number 500. But we will see that, hey, we have in that block, we have a block with 501 already. And this is one reason when we get invalid row ID, which is essentially the same reason like this, it's like the same thing like the object no longer exists, but it's a slightly different scenario. When the index is still there, nobody has overwritten the index blocks yet, but the table blocks are overwritten. And then this sanity check of does that block actually have the data block ID or data object ID what our index had in it? Does it still match? And it doesn't. And this is when you get this error. Of course, sometimes this error comes because of a corruption, but not always. So if you are doing truncates and drops and partition exchanges and alter table or partition moves while you have long-running queries, and if you see these errors, well, that's likely the reason. Try to do these exchanges and these operations during a quieter time, or at least when you're dropping, well, don't drop during the daytime, drop during a quieter time. And when doing partition exchanges, the remaining tables which you exchange from a partition table, don't drop them immediately. If these issues are really bothering you. And usually when you have these errors, well, often you just rerun your query, and then, unless similar clash happens, then your query finishes okay. All right, so I'm already over time, so maybe I should have named this session as a 2-hour session which takes 4 hours or something like that. But let me take a sip of water, and then I'll just show you the small table threshold parameter, what I wanted to do, and I think then we can finish this. All right, so this is the reason. If you look at the MetaLink, then you see bugs related to that as well. But this is usually the reason, and the fundamental reason is that Oracle allows you to keep running your query even if you actually drop the table, or do DDL on the underlying table, which is kind of a good thing, because otherwise every time you would want to do a partition exchange or something, all your queries would somehow be cancelled or removed, return an error. Now you have a better chance. Okay. I already see that we won't talk much about object level checkpoints. We are not going to go into full detail, but I'm going to mention that in the context of this direct path read decision. So that's going to be the last thing I'm going to talk about. So basically we spoke about how the direct path reads, that Oracle decides, it opens up the segment header block for every partition what you access during the query, or every segment. When you access it via a full table scan or a fast full index scan, right? Fast full index scan is just like a full table scan, but on an index segment, discarding the branch blocks and so on. But anyway, Oracle decides whether a table is small or big based on a few things. One thing is the buffer cache size. So okay, so let's just verify. So let's start from $, buffer pool. Okay. Don't worry that there are slight mismatches, but and also there is, if you have a dynamic SGA, then your buffer cache may change. So this will further complicate issues. But basically I have to log on as sys because I'm gonna view undocumented parameters now. So okay, see, there is a parameter called small table threshold, which is automatically it's automatically calculated from your buffer cache size. So so let's see. So our let's say this buffer cache size in the buffer pool is this. So if I just say 199 divided by this total number of buffers from Dual, let's use Oracle as a calculator. So you see when I round it, it's 0.2. It's 2% roughly. So the the small table threshold is an fairly old parameter actually. It was previously used for deciding, even in Oracle 8.0 and 7.3 at times, it was used for deciding whether, if you did a full table scan, whether we should put the table blocks into the hot end of the LRU list or into the cold end. So if the table was a big table, it was bigger than the small table threshold, then the blocks went into the cold end. So they were kind of flushed out or replaced or reused, almost immediately. But when the table was considered a small one, then it was considered that its blocks were cached. They were put into the hot end of the LRU list. But in Oracle 8i, the whole LRU management changed to a touch count based mechanism. So basically Oracle just actually sees how frequently touched each buffer is in the buffer cache, and they ages out things based on that. But anyway, so the small table threshold is 2% of your buffer cache in blocks, right? So, and when the serial direct path read was introduced apparently in 11.1, then maybe we didn't fully test, but it seemed like that the logic was very simple. That basically, if the table was smaller than 5 times this, basically when you opened up the segment header, when your full scan row source in the execution plan, it opened up the segment header. It saw that, hey, the segment had, let's say, 1,000 blocks, right, under the high water mark. And now it compared this with the small table threshold, but there was a catch. It wasn't just small table threshold, it was actually times 5. So the direct path read decision is done by comparing this. So this 5 times this is 995. So if the table size was 1,000 blocks, and this calculation of 5 times, if this calculation is 995, right, then this table size is already bigger than this calculation. So if that particular table, if it was non-partitioned, or if it's partition table, then if that particular partition was 1,000 blocks, and it's actually bigger than 5 times small table threshold, then Oracle decided that, hey, this table is it's too big for caching. We don't want to poison the cache, or we don't want to flood the cache with all these big tables and potentially flushing out other smaller items. And this is when a direct path read decision was done. Okay, and Oracle doesn't switch. If it decides to do a direct path read for that segment, during this execution, then it will do it all the way to the end. It doesn't, in the sense, it doesn't scan through half of the table with direct path and then somehow stop and go into buffered mode. But if you rerun the query, maybe something has changed. the table has grown bigger. Actually, this is a good point. Let's say you see, if you follow the same example, let's say the table is 900 blocks. You see, it's smaller than this calculation, and buffered read would be used. So in the morning when I run my query, a buffered read is used. But in the evening, I already have that many blocks in the same table. It's the same table, same query, same optimizer stats, and even the same execution plan cached in library cache. Now I will reuse the same execution plan, which originally ended up using a buffered read because of the smaller amount of blocks. But now, in the evening, the same full scan row source opens up the segment header, and something has changed. Now we have 1001 blocks in that segment. And with the same execution plan, Oracle decides to use direct path read now. Because that segment header tells us a different number now. It's exactly the same execution plan. It hasn't been flushed out, for example. The plan hash value hasn't changed. Everything is the same. But now suddenly the query is doing direct path reads. So the execution plan is the same, but the I/O characteristics are completely different. And this is because direct path read is not a property of execution plan. So execution plan doesn't know anything about it. It doesn't even have a place for specifying whether to do a direct path read or not. This is a runtime decision done by a lower layer in Oracle. It's actually done by a data layer. So there is a function called KDST get rows or something like that. Or scan or something like that. So basically, this is done below at a lower layer than the execution plan. It's in the data layer already. Okay, so this was the simplistic approach. But when we looked further into this in 11.2, we started seeing weird stuff that sometimes the direct path read was used and sometimes it wasn't, and this calculation didn't really seem to work all the time. And what we found out is that Oracle started actually taking into account also that how cached this table is. So let's see if I can. I'm actually not going to reproduce that, so otherwise I'll just waste too much time. But Oracle nowadays actually can. It knows how many blocks of each segment are in cache. So basically, it still opens up this segment header. It sees how many blocks are in there. It knows how big the buffer cache is, and it also can query how many blocks of that segment are currently in cache. And this is, using a $KCBOQH. This is done during using this kind of $. Table. So these are things called you see, when you query $SGA stat, you see there are some memory structures called object queues, right? And I think there are some latches as well even. You see, object queue header operation is when you modify the queue and the linked list and so on. You see, the more physical reads you do, the more latch gets you have. And this is actually one case where you do a lot. If you do a lot of buffered physical reads, you may end up with this latch contention. If you have over 100 CPUs and all of them are doing lots of buffered full label scans, because they maintain this information, they protect this information here. And for every single object, so this should be the data object ID, we have a column called number of buffers. So basically, Oracle has an object queue for each segment which is currently loaded in buffer cache. It has a linked list which keeps track of all of the buffers which belong to that object. So this data is shown here, and this data is used by the and this direct path read decision, for example. So basically, Oracle sees that if I'm about to scan a partition which data object ID is 500, then it will go into this hash table here and look up object ID 500, and then it sees from here how many buffers of that object do we have in cache. So so this is one reason to use, one useful thing of that queue. So, and another reason, another place where this queue is used is segment level checkpoints. So this is, I just mentioned it, I'm going to talk about it some other day. So whenever you have the fast object checkpoint wait event or fast object reuse, and there is also one more, block range reuse checkpoint. So this is 11.202, I think. They have kind of you know, they make the checkpointing even more fine-grained. But basically, when you see these wait events, you know, these usually happen before you drop an object, or you truncate an object, or even alter table move, and also before. So this guy happens before you you know, do a direct path read, because Oracle has to flush all the, not flush, checkpoint all the dirty blocks, dirty buffers of that object what we are about to scan to disk, right? So these are the wait events what you see. This actually means that you are waiting for checkpoint who is waiting for DB writer to write only your objects dirty buffers to disk. And how do we know, you know, if the buffer cache is 1,000,000 buffers, right? You know, we don't want to scan through the whole buffer cache, right, and flush everything. You know, we only want to flush our partitions, dirty buffers. And this is where the object queue will be useful. We will actually use this kind of in-memory structure to find out how many buffers are on disk, and this is the pointer to the first dirty buffer, dirty block, or actually not just dirty, I think all of them. This is the pointer to the first buffer, which holds you know, holds a block of my partition, what I'm about to you know, scan or drop and so on. And then there will be follow-on pointers, so it's like a linked list. So you can actually query. I'm going to just finish with this little example that let's say big.2. So if I look into, so the data object ID of this big.2 is this 91 this something, right? Let's see how many blocks of that are in cache right now. So I can just, you know, the fastest way would be just to query this table. KCB OQH. Select. Interestingly, you know, I will only have one buffer. So this is the count, right? So it holds the count. You see, when I did a create table like that, then this used direct path insert as well. It didn't write anything into buffer cache. It did not flood the buffer cache. But why do we have one buffer, not 0 here? You know, we use the direct path load. Well, this one buffer is very likely at the segment header. So, so what I can do here now is I will just say alter system flush buffer cache, and well, this object is gone now from here. Let's do a select. Let's do a select count star from big2. Okay. So interestingly, we only see. Okay, so what is this? Let's query what the other. Why would you have 2 rows here? I just wondered whether this is because of the NUMA optimizations, and they actually have, the buffer cache is kind of internally split into more pieces. Let's see. We have two working sets. Aha, I think that's it. So if I do a select star from X $KCB VDS CWDS. Yeah. Okay. So so this is I had two working sets. So this is why I get two rows here. So we actually have we should add these numbers together. So this is the total number of buffers in the buffer cache. But I had two working sets, two DB writers, and like two buffer caches sort of. But anyway, so now we have a bunch of buffers in cache. So this is so this data is now used by the direct path read decision as well. So I don't know the exact algorithm, but basically if the buffer cache is, if the table is big, but most of its blocks are in buffer cache anyway. You open up the segment header, you see it's million blocks, and now you query this table. Now Oracle kind of reads it directly from the hash table and sees that 99% of the blocks are in cache anyway. So why no reason to do a direct path read. So then it will decide to do a buffered read. So now it can check not just the buffer cache size and the segment size, but also how many blocks of that segment are currently cached. So I think I wrote about it in the Exadata book as well. But basically, the small table threshold is that if the table is smaller than 5 times of this anyway, then it will do a buffered read. If there is another parameter which appeared recently, very large object threshold, again in the blocks. So so maybe there is a multiplier as well. I don't know that. It's a matter of testing out. But basically, if the segment size is bigger than that, then Oracle doesn't look into this, how many blocks are cached or not. Then it just will do this direct path read anyway. But if the segment size is somewhere in between 5 times this and this number, or probably maybe 5 times this as well, maybe there is some other multiplier. If the size is somewhere in the between of this range, then it will check how many blocks are actually cached. All right. And now something in 11.202. Let me look. There is one interesting thing. So I told you one thing that Oracle always opens up the segment header. So if you have 1 million partitions, then you will open 1 million. You probably have like pretty much for every segment, every partition and all the indexes on it, you will have the segment headers in buffer cache. And you still have single block reads occasionally happening because you have to open the segment header. And let's see, so this has changed in 11.202, and I just want to find out where the parameter is, and then I'm done. I have well, I think I got a blog about it. I don't want to waste your time here. Okay, so anyway, so they have improved something that actually Oracle can use optimizer stats now for deciding whether to do a direct path read or buffered read. But it's not, again, it's not just done during the optimization phase. It's still not part of the execution plan. So it's the only difference is that instead of opening the segment header block, instead of that, we will open the Oracle will go into the data dictionary cache for every segment, and read the number of blocks from there, which can be sort of outdated, if you haven't gathered stats for a while. Anyway, so I'll just find out where it is, and I'll blog about it. And it's not from system stats, so I see there was a question. Let me just look into it. Now I'm kind of size. Nope. Count. Yeah, don't remember. It's somewhere in my notes. I may have even written about it in the Exadata book. I don't remember anymore. Okay, so so I think there are too many questions to answer. I think I'm actually gonna skip all of them. Sorry about that. So if you still, I think some of them I probably answered, while I was going on, continuing with the material. But what you can do if you still have a question which I didn't answer and you want to get the answer, please ask it again in my blog, so I can kind of respond to them later on. Okay. Yeah, I think that's it. I see so many questions, so many interesting things to talk about. Okay, so well, some of you are still online, so I'll just remind you that I will do more of these sessions because I like them, because it's easier than writing stuff. I easily spend 4 hours writing a single article. I think I can actually give more out that way. If you are, if you have vlogs, feel free to write some summary about what I spoke here. I will post the video in the blog as well. If not today, then tomorrow. So I just want to show you. This is the Exadata book, which you can buy if you are interested in more stuff in the Exadata context. Then in Exadata context, the important thing here is that how direct path reads are chosen. If direct path reads are chosen, then smart scans have a chance of actually working and kicking in. Unless you hit some other problems, direct path read means a smart scan on Exadata. But of course, you have bugs and special cases where Oracle, falls back to the block IO mode again. If you read the book, we have explained this in detail as well. And read my blog. Also, I would like to point your attention here that I do online training as well. And about also in September, I'll do the parallel execution and partitioning sessions, where I will kind of revisit this direct path reads as well in the context of parallel execution and so on. And I think that's all. Just stay tuned and wait for the video. And any comments and feedback is going to be welcome. And also, I think there is more. I didn't cover everything well enough here, so there will be future events. So thanks very much, and I'm going to go and open my beer now and try to not spill it anywhere.